In this module, you will understand the mechanism of flight and analyze performance of DFS and Unicorn Phoenix. The DFS methodology and Unicorn Phoenix software enables high Reynolds number aerodynamic simulation at high efficiency by adaptive error control, large time steps, and a slip wall model with 3D slip separation mechanism. This allows time-dependent simulation of a full aircraft in just a few hours compared to weeks using standard methods, and an easy understanding of the fantastic mechanism of flight. We can understand slightly viscous bluff body flow, such as flight, as a zero drag and lift potential flow modified by 3D slip separation instability of potential flow into turbulent flow with non-zero drag and lift. In our course, you will have the opportunity to carry out detailed adaptive DFS in Unicorn Phoenix, validating the theory for wings and full aircraft, as well as several other model and complex problems. The aerodynamic forces on a wing or an aircraft are simply the mean in time of the surface integral of the pressure weighted by the normal, as you can see here. To understand the mechanism of flight, we look at computed solutions. Here at the low angle of attack, where we see high velocity and low pressure at the leading edge, and slip separation at the trailing edge. This detailed surface pressure plot shows the low pressure suction at the leading edge. For higher angle of attack, we observe stall, where the flow separates at the leading edge, removing the low pressure suction and giving large drag due to the large wake. We now analyze the performance gains by DFS and Unicorn Phoenix. We start with adaptive error control. Uniform refinement grows as h to the -3. That means that refining the mesh once increases the degrees of freedom by a factor 8. To reach the desired accuracy, we have to drive down the mesh size everywhere, requiring enormous cost. In contrast, adaptivity allows a minimal number of degrees of freedom, on the order of resolving the geometry for about 5% accuracy that we have seen, about 1 million mesh points. The large time step formulation in DFS and Unicorn Phoenix allows 100 to 1,000 times larger time steps than standard methods. The slip wall model gives enormous efficiency gain by avoiding having to resolve a very thin boundary layer of cost Reynolds number to the power of 2, which gives about 10 to the 16 mesh points, which is impossible even for the largest supercomputers today for a full aircraft. Thank you for your attention.